So maybe this is a good chance to step back. You mentioned OpenCog 2.0, but
go back to OpenCog 0.0, which exists
alpha.
now.
Yeah. Maybe talk through the history of OpenCog and your thinking about these ideas.
I would say OpenCog 2.0 is a term worth throwing around sort of tongue-in-cheek because the existing OpenCog system that we're working on now is not remotely close to what we'd consider a 1.0, right? I mean it's an early it's been around 13 years or something, but it's still an early stage research system, right? And actually we are going back to the beginning in terms of theory and implementation because we feel like that's the right thing to do. But I'm sure what we end up with is going to have a huge amount in common with the current system. I mean, we all still like the general approach. So
first of all, what is OpenCog?
Sure. OpenCog is an open source software project that I launched together with several others in 2008. And probably the first code written toward that was written in 2001 or 2 or something that was developed as a proprietary code base within my AI company, Novamente LLC. Then we decided to open source it in 2008, cleaned up the code, threw out some things, added some new things. And
what language is it written in?
It's C++. Primarily, there's a bunch of Scheme as well, but most of it's C++.
Nice. And it's separate from that. Something we'll also talk about is SingularityNET. So it was born as a non-networked thing.
Correct. Well, there are many levels of networks involved here, right?
No connectivity to the internet. Or no?
Well,
at birth.
Yeah. I mean, SingularityNET is a separate project and a separate body of code. And you can use SingularityNET as part of the infrastructure for a distributed OpenCog system. But there are different layers. Yeah.
Got it.
So OpenCog, on the one hand, as a software framework, could be used to implement a variety of different AI architectures and algorithms. But in practice, there's been a group of developers, which I've been leading together with Linus Vepstas, Neil Geisweiler, and a few others, which have been using the OpenCog platform and infrastructure to implement certain ideas about how to make an AGI. So there's been a little bit of ambiguity about OpenCog, the software platform, versus OpenCog, the AGI design. Because in theory, you could use that software you could use it to make a neural net. You could use it to make a lot of different AGI.
What kind of stuff does the software platform provide? Like in terms of utilities tools, like what?
Yeah, let me first tell about OpenCog as a software platform, and then I'll tell you the specific AGI R&D we've been building on top of it.
Yep.
So the core component of OpenCog as a software platform is what we call the atom space, which is a weighted labeled hypergraph.
ATOM, atom space.
Atom
right?
space, yeah. Not Adam, like Adam and Eve, although that would be cool too. But, yeah, so you have a hypergraph, which is like a graph in this sense is a bunch of nodes with links between them. A hypergraph is like a graph, but links can go between more than 2 nodes. So you have a link between 3 nodes. And in fact, OpenCog's atom space would properly be called a metagraph because you can have links pointing to links, or you could have links pointing to whole subgraphs, right? So it's an extended hypergraph or a metagraph. And
is metagraph a technical term?
It is now a technical term.
Interesting.
But I don't think it was yet a technical term when we started calling this a generalized hypergraph. But in any case, it's a weighted labeled generalized hypergraph or weighted labeled metagraph. The weights and labels mean that the nodes and links can have numbers and symbols attached to them. So they can have types on them. They can have numbers on them that represent, say, a truth value or an importance value for a certain purpose.
And of course, like with all things, you can reduce that to a hypergraph, and then the hypergraph can be reduced
to a hypergraph to a graph, and you could reduce a graph to an adjacency matrix. Right. So, I mean, there's always multiple representations.
But there's a layer of representation that seems to work well here. Got it.
Right. And so similarly, you could have a link to a whole graph, because a whole graph could represent, say, a body of information.
Yeah.
And I could say, I reject this body of information. Then one way to do that is make that link go to that whole subgraph representing the body of information, right? I mean, there are many alternate representations, but that's, anyway, what we have in OpenCog, we have an atom space, which is this weighted labeled generalized hypergraph. Knowledge store, it lives in RAM. There's also a way to back it up to disk. There are ways to spread it among multiple different machines. Then there are various utilities for dealing with that. So there's a pattern matcher, which lets you specify a sort of abstract pattern and then search through a whole atom space weighted labeled hypergraph to see what sub-hypergraphs may match that pattern, for an example. So then there's something called the COG server in OpenCog, which lets you run a bunch of different agents or processes in a scheduler, and each of these agents, basically it reads stuff from the atom space and it writes stuff to the atom space. So this is sort of the basic operational model. Like
that's the software framework there.
Right. And of course there's a lot there just from a scalable software engineering standpoint.
So you could use this. I don't know if have you looked into the Stephen Wolfram's physics project recently with the hypergraphs and stuff? Could you theoretically use like the software framework to play?
You certainly could, although Wolfram would rather die than use anything but Mathematica for his work.
Well, but there's a big community of people who are, would love integration. And like you said, the young minds love the idea of integrating, of connecting things.
That's right. And I would add on that note, the idea of using hypergraph type models in physics is not very new. Like if you look at...
The Russians did it first.
Well, I'm sure they did. And a guy named Ben Drybus, who's a mathematician, a professor in Louisiana or somewhere, had a beautiful book on quantum sets and hypergraphs and algebraic topology for discrete models of physics, and carried it much farther than Wolfram has. But he's not rich and famous, so it didn't get in the headlines. But yeah, Wolfram aside, certainly that's a good way to put it. The whole OpenCog framework, you could use it to model biological networks and simulate biology processes. You could use it to model physics on discrete graph models of physics. So you could use it to do, say, biologically realistic neural networks, for example. And that's a framework.
What do agents and processes do? Do they grow the graph? What kind of computations, just to get a sense, are they supposed to do?
In theory, they could do anything they want to do. They're just C++ processes. On the other hand, the computation framework is sort of designed for agents where most of their processing time is taken up with reads and writes to the atom space. And so that's a very different processing model than, say, the matrix multiplication based model as underlies most deep learning systems, right? So you could create an agent that just factored numbers for 1 billion years. It would run within the OpenCog platform, but it would be pointless, right? The point of doing OpenCog is because you want to make agents that are cooperating via reading and writing into this weighted labeled hypergraph, right? And that has both cognitive architecture importance, because then this hypergraph is being used as a sort of shared memory among different cognitive processes, but it also has, software and hardware implementation implications, because current GPU architectures are not so useful for OpenCog, whereas a graph chip would be incredibly useful, right? And I think GraphCore has those now, but they're not ideally suited for this. But I think in the next, let's say, 3 to 5 years, we're going to see new chips where like a graph is put on the chip, and the back and forth between multiple processes acting SIMD and MIMD on that graph is going to be fast. And then that may do for OpenCog type architectures what GPUs did for deep neural architectures.
As a small tangent, can you comment on thoughts about neuromorphic computing? So like hardware implementations of all these different kind of... are you interested? Are you excited by that possibility?
I'm excited by graph processors because I think they can massively speed up speed up
OpenCog type of stuff.
OpenCog, which is a class of architectures that
Now,
I'm working on. I think if in principle, neuromorphic computing should be amazing. I haven't yet been fully sold on any of the systems that are out there. Like memristors should be amazing too, right? So a lot of these things have obvious potential, but I haven't yet put my hands on a system that seemed to manifest that.
Marxism
that
should be amazing, but the current systems have not been great.
I mean, look, for example, if you wanted to make a biologically realistic hardware neural network, like making a circuit in hardware that emulated like the Hodgkin-Huxley equation or the Izhikevich equation, like equate differential equations for a biologically realistic neuron, and putting that in hardware on the chip, that would seem that it would make more feasible to make a large-scale, truly biologically realistic neural network. Now, what's been done so far is not like that. So I guess personally, as a researcher, I mean, I've done a bunch of work in computational neuroscience, where I did some work with IARPA in DC, Intelligence Advanced Research Project Agency. We were looking at how do you make a biologically realistic simulation of 7 different parts of the brain cooperating with each other using like realistic nonlinear dynamical models of neurons, and how do you get that to simulate what's going on in the mind of a geoint intelligence analyst while they're trying to find terrorists on a map, right? So if you want to do something like that, having neuromorphic hardware that really let you simulate like a realistic model of the neuron would be amazing. But that's sort of with my computational neuroscience hat on, right? With an AGI hat on, I'm just more interested in these hypergraph knowledge representation based architectures, which would benefit more from various types of graph processors, because the main processing bottleneck is reading and writing to RAM. It's reading and writing to the graph in RAM. The main processing bottleneck for this kind of proto-AGI architecture is not multiplying matrices. And for that reason, GPUs, which are really good at multiplying matrices, don't apply as well. There are frameworks like Gunrock and others that try to boil down graph processing to matrix operations, and they're cool, but you're still putting a square peg into a round hole in a certain way. And the same is true. I mean, current quantum machine learning, which is very cool. It's also all about how to get matrix and vector operations in quantum mechanics. And I see why that's natural to do. I mean, quantum mechanics is all unitary matrices and vectors, right? On the other hand, you could also try to make graph-centric quantum computers, which I think is where things will go. And then we can make, like, take the OpenCog implementation layer, implement it in an uncollapsed state inside a quantum computer. But that may be the singularity squared, right? I'm not sure we need that to get to human level.
Singularity squared.
Human level.
That's already beyond the first singularity. But can we just
let's go back to OpenCog.
No, but and the hypergraph and OpenCog.
Yeah. That's the software framework, right? So then the next thing is our cognitive architecture tells us particular algorithms to put there.
Got it. Can we backtrack on the kind of is this graph designed? Is it in general supposed to be sparse, and the operations constantly grow and change the graph?
Yeah, the graph is sparse.
But is it constantly adding links and so on?
It is a self-modifying hypergraph.
So it's not. So the write and read operations you're referring to, this isn't just a fixed graph to which you change the way. It's just constantly growing graph.
Yeah, that's true. So it is different model than, say, current deep neural nets tend to have a fixed neural architecture, and you're updating the weights. Although there have been like cascade correlational neural net architectures that grow new nodes and links, but the most common neural architectures now have a fixed neural architecture. You're updating the weights, and in OpenCog you can update the weights, and that certainly happens a lot. But adding new nodes, adding new links, removing nodes and links is an equally critical part of the system's operations.
Got it. So now when you start to add these cognitive algorithms on top of this OpenCog architecture, what does that look like? So what?
Yeah, so that within this framework then, creating a cognitive architecture is basically two things. It's choosing what type system you want to put on the nodes and links in the hypergraph, what types of nodes and links you want, and then it's choosing what collection of agents, what collection of AI algorithms or processes are going to run to operate on this hypergraph. And of course, those two decisions are closely connected to each other. So in terms of the type system, there are some links that are more neural net-like. They're just like have weights to get updated by Hebbian learning and activation spreads along them. There are other links that are more logic-like and nodes that are more logic-like. So you could have a variable node, and you can have a node representing a universal or existential quantifier, as in predicate logic or term logic. So you can have logic-like nodes and links, or you can have neural-like nodes and links. You can also have procedure-like nodes and links, as in, say, combinatorial logic or lambda calculus representing programs. So you can have nodes and links representing many different types of semantics, which means you could make a horrible, ugly mess, or you could make a system where these different types of knowledge all interpenetrate and synergize with each other beautifully, right?
So the hypergraph can contain programs.
Yeah, it can contain programs, although it can, in the current version, it is a very inefficient way to guide the execution of programs, which is one thing that we are aiming to resolve with our rewrite of the system now.
So what to you is the most beautiful aspect of OpenCog? Just to you personally, some aspect that captivates your imagination, from beauty or power? Yeah.
What fascinates me is finding a common representation that underlies abstract declarative knowledge and sensory knowledge and movement knowledge and procedural knowledge and episodic knowledge, finding the right level of representation where all these types of knowledge are stored in a sort of universal and interconvertible yet practically manipulable way, right? So that's to me that's the core, because once you've done that, then the different learning algorithms can help each other out. Like, what you want is, if you have a logic engine that helps with declarative knowledge, and you have a deep neural net that gathers perceptual knowledge, and you have, say, an evolutionary learning system that learns procedures, you want these to not only interact on the level of sharing results and passing inputs and outputs to each other, you want the logic engine, when it gets stuck, to be able to share its intermediate state with the neural net and with the evolutionary learning algorithm, so that they can help each other out of bottlenecks and help each other solve combinatorial explosions by intervening inside each other's cognitive processes. But that can only be done if the intermediate state of a logic engine, an evolutionary learning engine, and a deep neural net are represented in the same form. And that's what we figured out how to do by putting the right type system on top of this weighted labeled hypergraph.
So can you maybe elaborate on what are the different characteristics of a type system that can coexist amongst all these different kinds of knowledge that needs to be represented? And is it hierarchical? Just any kind of insights you can give on that kind of type system.
Yeah. So this gets very nitty gritty and mathematical, of course. But one key part is switching from predicate logic to term logic.
What is predicate logic? What is term logic?
So term logic was invented by Aristotle, or at least that's the oldest recollection we have of it. But term logic breaks down basic logic into basically simple links between nodes, like an inheritance link between node A and node B. So in term logic, the basic deduction operation is A implies B, B implies C, therefore A implies C. Whereas in predicate logic, the basic operation is modus ponens, like A implies B, therefore B. So it's a slightly different way of breaking down logic. But by breaking down logic into term logic, you get a nice way of breaking logic down into into nodes and links. So your concepts can become nodes, the logical relations become links. And so then inference is like, so if this link is A implies B, this link is B implies C, then deduction builds a link A implies C. And your probabilistic algorithm can assign a certain weight there. Now, you may also have like a Hebbian neural link from A to C, which is the degree to which A being the focus of attention should make B the focus of attention, right? So you could have then a neural link, and you could have a symbolic, like logical inheritance link in your term logic, and they have separate meaning, but they could be used to guide each other as well. Like if there's a large amount of neural weight on the link between A and B, that may direct your logic engine to think about, well, what is the relation? Are they similar? Is there an inheritance relation? Are they similar in some context? On the other hand, if there's a logical relation between A and B, that may direct your neural component to think, well, when I'm thinking about A, should I be directing some attention to B also, because there's a logical relation. So in terms of logic, there's a lot of thought that went into how do you break down logic relations, including basic sort of propositional logic relations, as Aristotelian term logic deals with, and then quantifier logic relations also. How do you break those down elegantly into a hypergraph? Because you can boil logic expressions into a graph in many different ways. Many of them are very ugly, right?
Right.
We tried to find elegant ways of sort of hierarchically breaking down complex logic expression into nodes and links, so that if you have, say, different nodes representing, Ben, AI, Lex, interview, or whatever, the logic relations between those things are compact in the node and link representation, so that when you have a neural net acting on those same nodes and links, the neural net and the logic engine can sort of interoperate with each other.
And also interpretable by humans? Is that an important...
That's tough. Yeah, in simple cases, it's interpretable by humans. But honestly, I would say logic systems give more potential for transparency and comprehensibility than neural net systems, but you still have to work at it. Because, if I show you a predicate logic proposition with like 500 nested universal and existential quantifiers and 217 variables, that's no more comprehensible than the weight matrix of a neural network, right? So I'd say the logic expressions that an AI learns from its experience are mostly totally opaque to human beings, and maybe even harder to understand than a neural net. Because, when you have multiple nested quantifier bindings, it's a very high level of abstraction. There is a difference, though, in that within logic, it's a little more straightforward to pose the problem of like normalize this and boil this down to a certain form. You can do that in neural nets too. Like you can distill a neural net to a simpler form, but that's more often done to make a neural net that'll run on an embedded device or something. It's harder to distill a net to a comprehensible form than it is to simplify a logic expression to a comprehensible form. But it doesn't come for free. Like what's in the AI's mind is incomprehensible to a human unless you do some special work to make it comprehensible. So on the procedural side, there's some different and sort of interesting voodoo there. If you're familiar in computer science, there's something called the Curry-Howard correspondence, which is a one-to-one mapping between proofs and programs. So every program can be mapped into a proof. Every proof can be mapped into a program. You can model this using category theory and a bunch of nice math. But we want to make that practical, right? So that if you have an executable program that like moves a robot's arm or figures out in what order to say things in a dialogue, that's a procedure represented in OpenCog's hypergraph. But if you want to reason on how to improve that procedure, you need to map that procedure into logic using Curry-Howard isomorphism, so that then the logic engine can reason about how to improve that procedure and then map that back into the procedural representation that is efficient for execution. So again, that comes down to not just can you make your procedure into a bunch of nodes and links, because that can be done trivially. A C++ compiler has nodes and links inside it. Can you boil down your procedure into a bunch of nodes and links in a way that's like hierarchically decomposed and simple enough.
You can reason about.
Yeah, that given the resource constraints at hand, you can map it back and forth to your term logic, like fast enough and without having a bloated logic expression, right? So there's just a lot of nitty gritty particulars there. But by the same token, if you ask a chip designer, like, how do you make the Intel i7 chip so good? Right? There's a long list of technical answers there, which will take a while to go through, right? And this has been decades of work. I mean, the first AI system of this nature I tried to build was called WebMind in the mid-1990s, and we had a big graph operating in RAM implemented with Java 1.1, which was a terrible implementation idea. And then each node had its own processing. So like the core loop through all nodes in the network and let each node enact what its little thing was doing. And we had logic and neural nets in there, and evolutionary learning, but we hadn't done enough of the math to get them to operate together very cleanly. So it was quite a horrible mess. So as well as shifting an implementation where the graph is its own object and the agents are separately scheduled, we've also done a lot of work on how do you represent programs, how do you represent procedures, how do you represent genotypes for evolution in a way that the interoperability between the different types of learning associated with these different types of knowledge actually works. And that's been quite difficult. It's taken decades, and it's totally off to the side of what the commercial mainstream of the AI field is doing, which isn't thinking about representation at all, really. Although you could see, like in the DNC, they had to think a little bit about how do you make representation of a map in this memory matrix work together with the representation needed for, say, visual pattern recognition in a hierarchical neural network. But I would say we have taken that direction of taking the types of knowledge you need for different types of learning, like declarative, procedural, attentional, and how do you make these types of knowledge represent in a way that allows cross-learning across these different types of memory. We've been prototyping and experimenting with this within OpenCog, and before that, WebMind since the mid-1990s. Now, disappointingly to all of us, this has not yet been cashed out in an AGI system, right? I mean, we've used this system within our consulting business. So we've built natural language processing and robot control and financial analysis. We've built a bunch of sort of vertical market specific proprietary AI projects that use OpenCog on the back end, but we haven't. That's not the AGI goal, right? That's it's interesting, but it's not the AGI goal. So now what we're looking at with our rebuild of the system
2.0.
Yeah, we're also calling it True AGI, so we're not quite sure what the name is yet. That we made a website for trueagi.io, but we haven't put anything on there yet. So we may come up with an even better name. But
it's kind of like the real AI starting point for your AGI.
Yeah, but I like True better because True has like you can be true-hearted, right? You can be true to your girlfriend. So True has a number, and it also has logic in it, right? Because logic is a key part.
I like it. Yeah.
So yeah, with the True AGI system, we're sticking with this same basic architecture, but we're trying to build on what we've learned. And one thing we've learned is that we need type checking among dependent types to be much faster, and among probabilistic dependent types to be much faster. So as it is now, you can have complex types on the nodes and links, but if you want to put if you want types to be first-class citizens, so that you can have the types can be variables, and then you do type checking among complex higher-order types, you can do that in the system now, but it's very slow. This is stuff like is done in cutting-edge programming languages like Agda or something, these obscure research languages. On the other hand, we've been doing a lot tying together deep neural nets with symbolic learning. So we did a project for Cisco, for example, which was this was street scene analysis, but they had deep neural models for a bunch of cameras watching street scenes, but they trained a different model for each camera. because they couldn't get the transfer learning to work between camera A and camera B. So we took what came out of all the deep neural models for the different cameras, we fed it into an OpenCog symbolic representation. Then we did some pattern mining and some reasoning on what came out of all the different cameras within the symbolic graph. And that worked well for that application. I mean, Hugo Latapi from Cisco gave a talk touching on that at last year's AGI conference. It was in Shenzhen. On the other hand, we learned from there it was kind of clunky to get the deep neural models to work well with the symbolic system because we were using Torch, and Torch keeps a sort of computation graph, but you needed like real-time access to that computation graph within our hypergraph. And we certainly did it. Alexei Polipov, who leads our St. Petersburg team, wrote a great paper on cognitive modules in OpenCog, explaining sort of how do you deal with the Torch compute graph inside OpenCog. But in the end, we realized like that just hadn't been one of our design thoughts when we built OpenCog, right? So between wanting really fast dependent type checking and wanting much more efficient interoperation between the computation graphs of deep neural net frameworks and OpenCog's hypergraph, and adding on top of that, wanting to more effectively run an OpenCog hypergraph distributed across RAM in 10,000 machines, which is, we're doing dozens of machines now, but it's just not, we didn't architect it with that sort of modern scalability in mind. So these performance requirements are what have driven us to want to re-architect the base, but the core AGI paradigm doesn't really change. Like the mathematics is the same. It's just we can't scale to the level that we want in terms of distributed processing or speed of various kinds of processing with the current infrastructure that was built in the phase 2001 to 2008, which is hardly shocking, right?
Yeah.
So,
well, I mean, the three things you mentioned are really interesting. So, what do you think about in terms of interoperability, communicating with computational graph of neural networks? What do you think about the representations that neural networks form?
they're bad, but there's many ways that you could deal with that. So I've been wrestling with this a lot in some work on unsupervised grammar induction, and I have a simple paper on that I'll give at the next AGI conference, the online portion of which is next week, actually. So,
what is grammar induction?
So this isn't AGI either, but it's sort of on the verge between NeuroAI and AGI or something. Unsupervised grammar induction is the problem. Throw your AI system a huge body of text and have it learn the grammar of the language that produced that text. So you're not giving it labeled examples. So you're not giving it like 1,000 sentences where the parsers were marked up by graduate students. So it's just got to infer the grammar from the text. It's like the Rosetta Stone, but worse, right? Because you only have the one language, right?
Yeah.
And you have to figure out what is the grammar. So that's not really AGI because, I mean, the way a human learns language is not that, right? I mean, we learn from language that's used in context. So it's a social embodied thing. We see how a given sentence is grounded in observation.
There's
right?
an interactive element, I guess.
Yeah. On the other hand, so I'm more interested in that. I'm more interested in making an AGI system learn language from its social and embodied experience. On the other hand, that's also more of a pain to do. And that would lead us into Hanson Robotics and the robotics work I've done, which we'll talk about in a few minutes. But just as an intellectual exercise, as a learning exercise, trying to learn grammar from a corpus is very, very interesting, right? And that's been a field in AI for a long time. No one can do it very well. So we've been looking at transformer neural networks and tree transformers, which are amazing. These came out of Google Brain, actually. And actually, on that team was Lucas Kaiser, who used to work for me in the period 2005 through 8 or something. So it's been fun to see my former sort of AGI employees disperse and do all these amazing things. Way too many sucked into Google, actually. But yeah, anyway.
We'll talk about that too.
Yeah, Lucas Kaiser and a bunch of these guys, they create transformer networks, that classic paper like attention is all you need and all these things following on from that. So we're looking at transformer networks, and like these are able to, I mean, this is what underlies GPT-2 and GPT-3 and so on, which are very, very cool and have absolutely no cognitive understanding of any of the texts they're looking at. Like they're very intelligent idiots, right? But
sorry to take, but I'll bring us back. But do you think GPT-3 understands?
No,
language?
understands nothing. He's a complete idiot. But
So
it's
you
a
don't
brilliant idiot.
You don't think GPT 20 will understand language?
No.
So size is not going to buy you understanding.
And any more than a faster car is going to get you to Mars. Yeah.
Okay.
It's a completely different kind of thing. I mean, these networks are very cool. And as an entrepreneur, I can see many highly valuable uses for them. And as an artist, I love them, right? So, I mean, we're using our own neural model, which is along those lines, to control the Philip K. Dick robot now. And it's amazing to like train a neural model on the robot Philip K. Dick and see it come up with like crazed, stoned philosopher pronouncements, very much like what Philip K. Dick might have said, right? Like that. So these models are super cool. And I'm working with Hanson Robotics now on using a similar but more sophisticated one for Sophia, which we haven't launched yet. But so I think it's cool. But no,
it's not understanding.
These are recognizing a large number of shallow patterns. They're not forming an abstract representation, and that's the point I was coming to when we're looking at grammar induction. We tried to mine patterns out of the structure of the transformer network, and you can, but the patterns aren't what you want. They're nasty. So I mean, if you do supervised learning, if you look at sentences where you know the correct parts of a sentence, you can learn a matrix that maps between the internal representation of the transformer and the parse of the sentence. And so then you can actually train something that will output the sentence parse from the transformer network's internal state. And we did this, I think Christopher Manning, some others have now done this also. But I mean, what you get is that the representation is horribly ugly and is scattered all over the network and doesn't look like the rules of grammar that you know are the right rules of grammar, right? It's kind of ugly. So what we're actually doing is we're using a symbolic grammar learning algorithm, but we're using the transformer neural network as a sentence probability oracle. So like if you have a rule of grammar and you aren't sure if it's a correct rule of grammar or not, you can generate a bunch of sentences using that rule of grammar and a bunch of sentences violating that rule of grammar. And you can see the transformer model doesn't think the sentences obeying the rule of grammar are more probable than the sentences disobeying the rule of grammar. So in that way, you can use the neural model as a sentence probability oracle to guide a symbolic grammar learning process. And that's really interesting. That seems to work better than trying to milk the grammar out of the neural network that doesn't have it in there. So I think the thing is these neural nets are not getting a semantically meaningful representation internally by and large. So one line of research is to try to get them to do that. And Infogam was trying to do that. So like if you look back like 2 years ago, there was all these papers on like Edward, this probabilistic programming neural net framework that Google had, which came out of Infogam. So the idea there was like you could train an Infogam neural net model, which is a generative associative network, to recognize and generate faces, and the model would automatically learn a variable for how long the nose is, and automatically learn a variable for how wide the eyes are, or how big the lips are, or something, right? So it automatically learned these variables, which have a semantic meaning. So that was a rare case where a neural net trained with a fairly standard GAN method was able to actually learn a semantic representation. So for many years, many of us tried to take that the next step and get a GAN-type neural network that would have not just a list of semantic latent variables, but would have, say, a Bayes net of semantic latent variables with dependencies between them. The whole programming framework, Edward, was made for that. I mean, no one got it to work, right? And
do you think it's possible? Do you think
I don't know. It might be that backpropagation just won't work for it because the gradients are too screwed up.
Yeah.
Maybe you could get it to work using CMAES or some like floating point evolutionary algorithm.
Right.
We tried, we didn't get it to work. Eventually, we just paused that rather than gave it up. We paused that and said, well, okay, let's try more innovative ways to learn what are the representations implicit in that network without trying to make it grow inside that network. And I described how we're doing that in language. You can do similar things in vision, right? So
use it as an oracle.
Yeah. So you can. That's one way, is you use a structure learning algorithm, which is symbolic, and then you use the deep neural net as an oracle to guide the structure learning algorithm. The other way to do it is like Infogam was trying to do, and try to tweak the neural network to have the symbolic representation inside it. I tend to think what the brain is doing is more like using the deep neural net type thing as an oracle. Like, I think the visual cortex or the cerebellum are probably learning a non-semantically meaningful, opaque, tangled representation. And then when they interface with the more cognitive parts of the cortex is sort of using those as an oracle and learning the abstract representation. So if you do sports, say, take, for example, serving in tennis, right? I mean, my tennis serve is okay, not great, but I learned it by trial and error, right? And I mean, I learned music by trial and error too. I just sit down and play. But then if you're an athlete, which I'm not a good athlete, I mean, then you'll watch videos of yourself serving, and your coach will help you think about what you're doing, and you'll then form a declarative representation. But your cerebellum maybe didn't have a declarative representation. Same way with music. Like, I will hear something in my head, I'll sit down and play the thing like I heard it, and then I will try to study what my fingers did to see, like, what did you just play? Like, how did you do that, right?
Yeah.
Because if you're composing, you may want to see how you did it, and then declaratively morph that in some way that your fingers wouldn't think of, right? But the physiological movement may come out of some opaque, like, cerebellar reinforcement learned thing, right? And so that's, I think, trying to milk the structure of a neural net by treating it as an oracle may be more like how your declarative mind post processes what your visual or motor cortex. So, I mean, in vision, it's the same way. Like, you can recognize beautiful art much better than you can say why you think that piece of art is beautiful. But if you're trained as an art critic, you do learn to say why. And some of it's bullshit, but some of it isn't, right? Some of it is learning to map sensory knowledge into declarative and linguistic knowledge, yet without necessarily making the sensory system itself use a transparent and easily communicable representation.
Yeah, that's fascinating. To think of neural networks as like dumb question answers that you can just milk to build up a knowledge base. And then it could be multiple networks, I suppose, from different...
So I think if a group like DeepMind or OpenAI were to build AGI, and I think DeepMind is like 1,000 times more likely from what I could tell, because they've hired a lot of people with broad minds and many different approaches and angles on AGI, whereas OpenAI is also awesome, but I see them as more of like a pure deep reinforcement learning shop.
This time I got you.
So
there's
far,
a lot of there. You're right. There's there's so much interdisciplinary work at DeepMind, like neuroscience.
And you put that together with Google Brain, which granted they're not working that closely together now, but my oldest son Zarathustra is doing his PhD in machine learning applied to automated theorem proving in Prague under Joseph Urban. So the first paper, Deep Math, which applied deep neural nets to guide theorem proving, was out of Google Brain. Mm-hmm. I mean, by now the automated theorem proving community has gone way, way, way beyond anything Google was doing. But still, but anyway, if that community was going to make an AGI, probably one way they would do it was, take 25 different neural modules architected in different ways, maybe resembling different parts of the brain, like a basal ganglia model, cerebellum model, a thalamus module, a few hippocampus models, number of different models representing parts of the cortex, right? Take all of these and then wire them together to co-train and like learn them together like that. That would be an approach to creating an AGI. One could implement something like that efficiently on top of our true AGI, like OpenCog 2.0 system, once it exists. Although obviously Google has their own highly efficient implementation architecture. So I think that's a decent way to build AGI. I was very interested in that in the mid-90s. But, I mean, the knowledge about how the brain works sort of pissed me off. Like, it wasn't there yet. Like, you know, in the hippocampus, you have these concept neurons. Like the so-called grandmother neuron, which everyone laughed at it's actually there. Like I have some Lex Fridman neurons that fire differentially when I see you and not when I see any other person, right?
Yeah.
So how do these Lex Fridman neurons, how do they coordinate with the distributed representation of Lex Fridman I have in my cortex, right? There's some back and forth between cortex and hippocampus that lets these discrete symbolic representations in hippocampus correlate and cooperate with the distributed representations in cortex. This probably has to do with how the brain does its version of abstraction and quantifier logic, right? Like you can have a single neuron in the hippocampus that activates a whole distributed activation pattern in cortex. Well, this may be how the brain does like symbolization and abstraction, as in functional programming or something, but we can't measure it. Like we don't have enough electrodes stuck between the cortex and the hippocampus in any known experiment to measure it. So I got frustrated with that direction, not because it's impossible.
Because we just don't understand enough yet.
We don't. Of course, it's a valid research direction. You can try to understand more and more, and we are measuring more and more about what happens in the brain now than ever before. So it's quite interesting. On the other hand, I sort of got more of an engineering mindset about AGI. I'm like, well, okay, we don't know how the brain works that well. We don't know how birds fly that well yet either. We have no idea how a hummingbird flies in terms of the aerodynamics of it. On the other hand, we know basic principles of like flapping and pushing the air down, and we know the basic principles of how the different parts of the brain work. So let's take those basic principles and engineer something that embodies those basic principles, but is well designed for the hardware that we have on hand right now.
Yeah. So do you think we can create AGI before we understand how the brain works?
I think that's probably what will happen. And maybe the AGI will help us do better brain imaging that will then let us build artificial humans, which is very, very interesting to us because we are humans, right?
Yeah.
I mean, building artificial humans is super worthwhile. I just think it's probably not the shortest path to AGI.
So it's a fascinating idea that we would build AGI to help us understand ourselves. A lot of people ask me if, the young people interested in doing artificial intelligence, they look at sort of, doing graduate level, even undergrads, but graduate level research. And they see where the artificial intelligence community stands now. It's not really AGI type research for the most part.
Yeah.
So the natural question they ask is, what advice would you give? I mean, maybe I could ask if people were interested in working on OpenCog or in some kind of direct or indirect connection to OpenCog or AGI research, what would you recommend?
OpenCog, first of all, is open source project. There's a Google group discussion list. There's a GitHub repository. So if anyone's interested in lending a hand with that aspect of AGI, introduce yourself on the OpenCog email list. And there's a Slack as well. I mean, we're certainly interested to have inputs into our redesign process for a new version of OpenCog, but also we're doing a lot of very interesting research. I mean, we're working on data analysis for COVID clinical trials. We're working with Hanson Robotics. We're doing a lot of cool things with the current version of OpenCog now. So there's certainly opportunity to jump into OpenCog or various other open source AGI-oriented projects.
So would you say there's like master's and PhD theses in there?
Plenty, of course. I mean, the challenge is to find a supervisor who wants to foster that sort of research. But it's way easier than it was when I got my PhD,
For sure.
right?